Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Imagine standing before a massive, centuries-old cathedral, its stone walls towering above you, silent, majestic, and seemingly eternal. Yet, hidden within that ancient rock is a conversation we rarely hear, the acoustic signature of stone. This secret language, deciphered by geophysicists, tells us not just about the stone's history, but about its future, specifically, whether it's planning to collapse. Since antiquity, master builders relied on instinct and empirical knowledge to judge the health of their materials. If a block of stone sounded dull when struck, it might be discarded, perhaps indicating a hidden fissure. Modern science has formalized this intuition into a powerful diagnostic tool. Non-destructive testing, or NDT, applied through the lens of geophysical acoustics. Ancient architecture, whether it's a Roman aqueduct, a Mayan pyramid, or a Gothic cathedral, faces the same fundamental enemies: gravity, water, and time. Over hundreds, sometimes thousands of years, microfractures propagate, water freezes and expands, and internal voids form due to differential settling or decay of mortar. These processes weaken the structure from the inside out, often giving no visible warning until it's too late, resulting in catastrophic failure. The challenge for conservationists is how to peer deep into a massive stone wall without taking a core sample or tearing the structure apart. This is where geophysics steps in, borrowing techniques typically reserved for mapping underground oil reserves or studying earthquake zones. The key technology here is seismic or acoustic tomography. The concept is elegantly simple. Everything has a sound speed. A healthy, dense block of limestone transmits sound waves, specifically P waves, or compressional waves, at a rapid, predictable speed. But if that stone is riddled with cracks, saturated with water, or contains large internal air pockets, the wave transmission speed drastically slows down or the energy is scattered and attenuated. To conduct this test, researchers carefully place a grid of sensors, known as geophones or accelerometers, across the surface of the structure. A small, controlled mechanical impact, a simple tap or a mild pulse generated by a specialized hammer, is initiated at a specific point. The resulting acoustic energy travels through the structure, and the geophones record exactly when the waves arrive at their various locations. By measuring the travel time from the source to each sensor, scientists can create a three-dimensional map, a tomogram, of the interior structure. Areas where the waves slow down correspond precisely to damage, voids, or material degradation. This velocity anomaly acts as the stone's secret whisper of distress. It's the acoustic signature of failure, detected perhaps decades before the visible signs of cracking emerge. Think of it like an MRI for stone. Instead of hydrogen atoms, we are mapping wave velocity. If the wave hits an air-filled void, it's like a sudden speed bump, flagging a high-risk area requiring immediate, targeted repair. This technique is absolutely vital for monuments that need to remain structurally intact, like UNESCO World Heritage Sites. For example, applying this method to the massive foundational columns of the Parthenon could reveal whether internal corrosion from past, improperly installed iron supports is still propagating. Or perhaps, detecting hidden moisture pockets deep within the load-bearing walls of a medieval castle, which could lead to inevitable spalling and collapse if left unchecked. The blending of ancient construction wisdom with modern seismic technology provides a profound new layer of preservation. We are moving beyond mere surface conservation to deep, non-invasive diagnosis. The acoustic signature of stone is a finite resource. Once the integrity is compromised, the ancient structure's ability to bear its load decreases irreversibly. By learning to listen to these deep, subterranean sounds, we are giving a voice to the silent architects of the past, ensuring their monumental works endure far into the future. This is not just high-tech maintenance, it is a critical dialogue between the materials of antiquity and the engineering of tomorrow. The ability to detect internal pathology based purely on how sound travels through matter fundamentally shifts how we manage and preserve our global heritage. It allows us to be proactive, rather than reactive, to the inevitable ravages of time. For more incredible facts like this, don't forget to subscribe and turn on notifications.